Good afternoon, everybody. Let's get started. So, welcome to 6004, Fall 2019 edition. I am Daniel Sanchez, and together with Silvina Hanano-Wachman and Jason Miller, we will be your instructors this term. We're very excited to offer this course again, and we hope you enjoy taking it as much as we enjoy teaching it. Together with us, we also have an amazing team of TAs. So please stand up so that students can see you. So we have Kathy, Brian, Felipe, Juan, Dominic, Elena, Sebastian, and Kendall. And they will all be helping you with labs, design projects, and also recitation sections. They are also responsible for keeping all the infrastructure in the course running. Okay. So this course is an introduction to the world of digital systems, right? And digital systems, it seems like they've been around for a while, but in the grand scheme of things, they're actually fairly new. So this is how computing devices or digital devices look like at the dawn of the digital era, just 75 years ago. This in particular is a picture of the ENIAC, which was built in 1943. Weighed 30 tons, took a couple of rooms. When you turn it on, it consumed 200 kilowatts. And for those 200 kilowatts, it could do 1,000 operations per second. This consumed so much power that it was deployed in Philadelphia, and so when they turned it on, the lights across the city dimmed down. Things have changed quite a bit since then, right? So we had these very slow, power-hungry, large, and also unreliable computers. This thing broke several times a day. And fast forward 75 years, if you look at a typical computer, a laptop in 2019, it weighs around a kilo, consumes around 10 watts, and performs around 10 billion operations per second. So, I like to make an analogy of what would happen if cars had improved at the same rate as compute power. So basically, today we would have cars that would travel at about the speed of light. Their efficiency would be of about 100,000 miles per gallon. And when you run out of fuel, you would just throw it away because its new car would be about $20. So, things have come a long way. But not only we have very powerful personal computers, computing is now everywhere, right? So we have smartphones, self-driving cars, sensor networks, that have these tiny embedded devices that are spread everywhere, drones, all sorts of embedded devices and appliances, and even very large data centers that power planet-scale internet services. And so, with all this growth in computing power, you might be wondering, well, don't we have enough? Don't we, aren't we good in terms of, how we reached a stable point in the amount of computing that we need? The answer is really no. And if you look at these systems, it's not only that we have a lot of power, but that because we have that vast and fast increase in power, every decade, new types of systems appear that use that power to create entirely new applications and drive computer science further into society. And so a lot of these system classes even didn't exist 10 years ago. Think of self-driving cars or even drones. Or they were dramatically different, right? The smartphone that you have in your pocket today is quite different from the smartphones from 2009. Okay, so in this course, what we're going to do is essentially bridge the gap between the physical world, devices, materials, and atoms, and computer programs. Essentially, we're going to see how computation is implemented in the physical world. And to do this, we're going to take a bottom-up approach, essentially building a stack of hardware and software. So we'll start with essentially learning about digital design, looking at combinational and sequential circuits that can solve particular problems. And then we will essentially use or build on these building blocks of combinational and sequential circuits to design a computer. A processor that can execute any computer program. We'll also look at caches and pipelining and other fundamental techniques to make these systems fast. And finally, we'll look at computer systems, right? How do we turn this very simple processor that's capable of running one program at a time and add both low-level software like an operating system and new hardware mechanisms like virtual memory to make it usable, to make it communicate with the outside world, to make different programs share the system safely. So, as I said before, these digital systems are evolving very, very quickly. They're also very complex, right? So, any chip today or any high-performance chip has north of 1 billion transistors. And how can you build anything that has 1 billion things in it while retaining a certain amount of speed, right? And so the answer to this is that between the layers in this stack, we have interfaces. We have bits and logic gates, digital circuits, an instruction set, and memory, and up at the top, what we call a virtual machine. And these interfaces are essentially very clean abstractions that let us hide the details of the implementation of each building block while still allowing us to reason about their behavior. So the benefit of these abstractions, of these interfaces, is that by shielding us from the implementation, we get to essentially evolve these technologies independently or with very loose coupling. And to also reuse all the investment that we've made in each of the layers, right? So you can take, for example, the programs that you coded for a computer built 50 years ago and run them on a system today. So basically, this leads to a style of design that is hierarchical, right? Where at each level, right, we have limited complexity, and then we hide the complexity through these abstractions. So, as I said, essentially you get these two benefits, right, from interfaces. You get the fact that you're hiding complexity, and then you can reuse and essentially leverage the investment that you've made at each level and have them evolve independently. Can any one of you tell me, some drawback of having this deep stack of technologies with these interfaces? In what case would you like to take a more direct approach and perhaps touch all the levels at the same time? Yes?
Having more levels leads to some inefficiencies because using the units on lower levels make some solutions which you might not need.
Exactly. So the problem in the end is performance, right? Is that there are multiple inefficiencies here because we're keeping a fixed interface that lives across generations. And so that's a trade-off. And in fact, what you'll see today is that with silicon fabrication technology slowing down, there's a lot of interest in breaking these interfaces, and actually, many companies today that traditionally we consider software companies like Google, Facebook, Amazon, and so on, they're all building their own custom hardware and essentially breaking through all these layers. So hardware design has become much, much more commonplace today. Okay, so in this course, interfaces are so important that we're going to start with one of them. We're going to start by studying assembly language and essentially looking at both what assembly language is. This is the language of general purpose computers, general purpose processors, where essentially you have a processor that's executing a sequence of instructions, each of which performs a simple operation. And then all high-level languages, C, Java, Python, through different translation mechanisms, eventually are executed and translated into a sequence of instructions and executed directly on hardware. And so we'll see how this process works so that you get a good sense of what is it that we're aiming to build. And then in the next 3 modules, we'll essentially take that bottom-up approach on the different layers of the stack that I showed you before. So we'll start with digital design, building combinational and sequential circuits, then computer architecture. We'll build both simple and slightly more complex but faster pipeline processors. We'll talk about the importance of the memory hierarchy. You cannot have both large and fast memories, and so that leads to caches, which are also a fundamental component of modern processors. And finally, we'll conclude with a module on computer systems, looking at operating systems, virtual memory, and issues around parallelism and synchronization. So as many of you know, today the only get to get good performance out of systems is to have them do a lot of things at once. And so we'll look at what that means for programs and also what that means for hardware, what sort of support you need if you want to build a system with multiple processing engines. Okay, so there are many, many different kinds of hardware that you could build with what we will learn in this course about hardware design. But we are focusing particularly on general purpose processors, right? On designing something that is essentially a very simple version of the processor that you all have today in your laptops, your cell phones, and so on. And there are 2 reasons for this. The first one is that microprocessors are the basic building block of computer systems. Even if you have all sorts of other chips, things like graphics processing units or other specialized designs, pretty much all computer systems are going to have some sort of general purpose processor. And so understanding these processors is crucial, even if you never go and design hardware again. The second nice feature of processors is that they are the most sophisticated digital systems today. So they have all the tricks, and they're actually a really good thing to study because all other types of digital hardware tend to pick tricks from the bag of tricks that were developed for general purpose processors. So understanding these systems will actually help you design all other kinds of hardware. And towards the tail of the course, we'll actually see how things like GPUs and other more specialized designs are just particular types of processors. So in this course, we take a methodology that essentially emphasizes learning by doing. So the best way to learn how these systems work is to actually build them. And so through labs and then a design project, by the end of the term, you will have designed a simple processor from scratch. Now, to do this, it is important to use modern design tools. And so processors today are incredibly complex. There are more engineers designing each Intel processor than there are engineers working on the latest Boeing plane. So there is a lot of engineering that goes into these systems. However, you alone are going to be able to design a processor from scratch. And the reason is that we're essentially using modern tools. On the one hand, we will use RISC-V, which is a simple and modern instruction set. If you know what an instruction set is, you might be familiar with X86, which is the most commonly used instruction set in laptops, or ARM, which is the most commonly used instruction set in cell phones and other embedded devices. We're going to use RISC-V, which is simpler, dramatically simpler than both of those, and is going to essentially let us get to the principles of assembly language without getting bogged down in complexity. And also, we will design hardware using Minispec. And this is a new addition this term. Minispec is a new hardware description language that I've built explicitly for 004. So a little bit of history. Over the past couple of years, we have changed this course to have a little bit more emphasis on using a modern hardware description language. Last year, we changed the course to use BlueSpec, which is a hardware description language that is very nice. It actually lets you do, design hardware very efficiently. However, it has some features that are quite advanced, and we saw that some students struggled with them. And so this term, we're trying a new language that is essentially a heavily simplified version of BlueSpec. And essentially, we have new tooling and a new compiler that hides all of those details and internally uses a lot of different tools. And so you'll be able to write your designs in Minispec, and then there will be a compiler and a certain tool chain that will produce both simulation executables and also will compile and synthesize circuits into gates that you can actually, you can measure the delay, the timing characteristics, the area that they take, all their physical properties. But you won't be exposed to any of that complexity. All right. So let's spend a few minutes talking about course mechanics. So there are 2 lectures per week, and all the materials for these lectures are available online. So you'll find handouts. We're recording lectures, and so you'll have the videos available shortly after the lecture, and also reference materials that cover all that we're going to discuss in the lectures. We have no required textbooks, but we have 2 optional textbooks, one of which covers the computer architecture side of the course, and the other that covers some of the digital design aspects of the course. If you want to buy one, I recommend that you buy the one on computer architecture, that is the computer organization and design. Okay, and then we'll have 2 recitations per week where you'll work through tutorial problems associated with each of the lectures using the skills and concepts from the previous lecture. And so in each recitation, depending on the content of the lecture, recitation instructors will also review and expand on some of the contents of the lecture. There are 7 mandatory lab exercises. The points between these lab exercises vary depending on the difficulty of the lab. Everything is done online, so you'll submit the lab online, and labs can be done in Athena, so you don't need to install any virtual machines or any software in your own laptops or in your own machines. But we ask you to come to lab and do a short check of meeting after you submit the lab, and that's just to check your understanding of the material. These labs will be due throughout the term. We will be releasing them 10 days to 2 to 3 weeks before they're due. And to give you some flexibility, you'll have 7 free late days so that you can hand these assignments or these labs later without incurring any penalty. After the 7 free late days, you lose 10% of the grade per day. So I heavily encourage you to not get into these heavy penalties that you get from late submissions. Okay, so there is one open-ended design project towards the end. So what we're going to do in the labs is essentially build relatively simple processors and programs, and then in the end, we'll look at how to make them really fast by putting everything together. And there are 3 quizzes. There is no final this term. The 3 quizzes are evening quizzes from 7:30 to 9:30 p.m. They're happening on October 17th, November 14th, and December 5th. If you have a conflict, please contact us at least 48 hours before to schedule a makeup. I saw a post on Piazza saying I have a conflict with quiz 3. Thanks for the early warning, but if you let us know the week before, that will be a little bit easier on us. Okay, in terms of recitations, there are 12 recitation sections on Wednesday and Friday, and each recitation section covers the material from the lecture in the previous day. If you have a conflict with your assigned section, just choose a different one. There's no need to let us know about changes in recitation sections. If you can make the section that you got assigned through the registrar, then perfect. But essentially what we're going to do is to ignore the assignments from the registrar at the beginning, and then as you'll settle down, we'll just keep track of which recitation are you attending. And the reason we do this is because we know a few of you have you're registered very recently, and so you don't have an assigned recitation, or you might have a conflict. That's okay. Just attend one of the recitations that works well with your schedule. Recitation attendance is mandatory, but it's self-mandatory, so it's worth 5% of your grade. That's not a lot, but it's enough to be worth going. And the reason that we make it mandatory is that we have consistently seen that students who attend recitations do significantly better in the course. So 6004 is not a spectator sport. Right? You'll get much more out of the course. You do the problems, and if you figure out how to do all the exercises that are associated with each lecture. That said, because we again want to give you flexibility, everyone has 4 excused absences. And finally, as I said, recitations will review lecture material and problems associated with this lecture. We recommend that you work on these problems before recitation. They're released together with the lecture slides, and they're available on the website. Some of these, since we understand that you don't have a lot of time to do all the problems in advance, we have some essential problems that are marked especially so that you can try just those before going to recitation. And then we will post solutions after each recitation. In terms of grading, basically 50% of the grade comes from labs and the design project, and 50% of the grade comes from quizzes and recitation attendance. There are 200 points total, right? 80 points from labs, 20 from the design project, 90 points from quizzes, that is 30 points per quiz, and then 10 points from recitation attendance. And we have fixed grade cutoffs. So this is a very transparent grading scheme. Grading, of course, is not curved. This depends on your performance. And so to get an A, you need to get at least 165 points. To get a B, at least 145. To get a C, at least 125. And if you get either less than 125 points or you don't complete all labs, you'll get an F. We do not give Ds in L04. And we also require you to pass the labs. You can submit the labs arbitrarily late, but you need to submit all the labs. Also note that the design project is worth the difference between a letter grade. So you can actually wait until you finish all the quizzes and figure out exactly how much work you want to put to get to the next letter grade. Or you could just do it in advance and do the best you can. Let me just say that the design project is going to be challenging. People very rarely get all the points, so don't bank on having all of the points. Okay, any questions? So we have a lot of online resources as well as offline resources to help you. The course website, as I mentioned, has up-to-date information on course policies, has all the handouts, has reference to supplemental readings for each lecture, which we recommend that you check out. And then we use Piazza extensively. This Piazza is the fastest way to get your questions answered, and we will post all course announcements on Piazza. So we expect you to sign up. If you haven't done so yet, please sign up as soon as possible. Finally, we will also hold regular office hours in the lab. So we have room 32083 to help you with lab assignments, infrastructure, and any other questions that you might have. But primarily with lab assignments and check-off meetings. This room has a combination lock, which cannot appear on YouTube. So I will now go to this part of off screen. So a combination, in case you don't know, is very hard. All right, so please take note. Or just ask anyone who's already inside, because there's it's almost never empty. All right, finally, we want your feedback. We have gotten a lot of great feedback from students in previous years. That have really helped improve the course over time, and your input is really crucial to improve the course. Both this offering of the course as we move along, and also future versions. So we will have periodic informal surveys as we finish the different modules of the course to see how it's going. And anytime, feel free to email us or just post on Piazza. Okay, any questions so far? Good. So in the rest of the lecture, we're going to dive into the first technical topic in 004, which is binary encoding and binary arithmetic. And so, in digital systems, their key characteristic is, how they store information. So we'll figure out how to encode numbers in binary, and not only that, how to do so in a way that makes operating on these numbers, right, performing operations as addition and subtraction efficient. And this is going to essentially give us the necessary background to then, in the next lecture, dive into assembly language, right? So now that we have, coming out of this lecture, we'll have a good idea of what does it mean, to say that a computer stores numbers using ones and zeros, right? So, at a high level, the reason we call digital systems is that they store information and process information using digits, that is, discrete symbols. That's where the name digital comes from. And you could choose many different kinds of digits, right? You could have 2, 3, 4 kinds of different kinds of symbols, but most digital systems today use 2 binary digits, which are called bits in short. and we typically denote them as 0 and 1. And the reason we do this is that with current fabrication technology, we can implement operations like addition, like comparisons, like Boolean operations, and or exclusive or, and so on, very, very efficiently in hardware. But only if we represent these quantities using binary numbers. And so, as we will see, once we dive into digital devices, we'll see that the way that current systems store information is essentially as levels or ranges of voltages in different wires and components of the system. And so just picking two different ranges and encoding just two different symbols will make operation faster than if you were to pick 3 or 4 or 8 or more. But so now the question is, we're accustomed to representing things in base 10, right? So if specifically we first focus on how to represent integers. We need to do some things differently from how we represent numbers when we're manipulating them, right? Because we're using, we have 10 fingers, right? But which I guess is where base 10 mainly comes from. But if we're using two symbols, a few things are going to change. So let's start with positive integers. Let's say that you want to encode, or more precisely, non-negative integers. Let's say that you want to encode a positive integer using a sequence of bits. So the way we do this is we assign each bit a weight, right? So as you see here, bits have an associated weight, and going from right to left. So from right to left, weights are in increasing value, increasing powers of 2. So for example, the 11th digit here, counting from 0, has weight 2 to the 11, right? And then the value of an n-bit number, so the value of, for example, this string of digits over here, is given by the formula on the left, right? So it's 2 to the power of b, where b is the position counted from right to left, times the 0 or 1 value at that position. Okay, so just as an example, if we take this number, what value does it encode? Well, so if you want to translate, and in particular, what value does it encode in decimal, right, which is the base that we're all accustomed to. So to translate from binary to decimal, what we need to do is essentially expand this formula, right? So going from left to right, we'll start saying, well, what position is this? Well, this is position 11, or this is position 11, so there's 0 times 2 to the power of 11, plus 1 to the power 2 to the power of 10, plus 1 to 2 to the 9, times 2 to the 9, plus, and so on. And so you can expand this into 1024 plus 512 plus 256 plus 128 plus 64 plus 16, which happens to be 2000. Okay, how about the opposite? So if you wanted to translate from decimal to binary, right? Let's say that I give you number 11, and I ask you, what is its binary representation? So there's a very simple procedure where you essentially subtract the largest power of 2 that is smaller than this number repeatedly until you get to 0. So in this case, you'd have 11 minus 8, right? That's 3. And so that gives you 2 to the 3, right? And then 3 minus 2, that's 1. That gives you 2 to the power of 1, right? That's 2, 8. And then 1 minus 1 is 0, and so that gives you 2 to the 0. So putting these together, you get 1, 0, 1, 1. Right? Any questions? Oh, by the way, if you look at your handouts, everything that is in bright red, starting from this slide, is not there. That's just so that, rather than you reading along, you can do some of these together with me and essentially get a better understanding of things. That said, the slides that are online have everything available. So if you prefer that, you can also look there. Okay, so with this, what is the smallest number that we can represent? 0, right? That's all zeros. What is the largest number? 2 to the 12 minus 1, and in general we have n bits, that's 2 to the n minus 1. Perfect. Okay, so far so good. We just have one little issue here, which is that I don't want to be writing, 0, 1, 1, 1, 1, 1, 0, 1, 0, 0, 0, 0, right? It's just very tedious. So to be more succinct, we can use a notation that uses a base that's a power of 2. And in particular, we typically use hexadecimal notation, or hex for short. So in this case, what we do is we choose hex stands for base 16. And the nice thing about bases that are a power of 2 is that you can just take groups of bits and translate them. So this table shows you the translation between each group of 4 bits and its hex digit. Of course, because we only have 9 numbers, we start using letters at some point, and so you have digits 0 through 9 and then A through F. Don't worry, you'll learn this table by heart by the end of this course. And so to translate this into hexadecimal, this 12-bit binary number, you just take each particular group of bits and then translate it using this table, right? So you have 0, 0, 0, 0, that's hex digit 0. 1, 0, 1, 1, 0, 1, that's hex digit D. And then 0, 1, 1, 1, that's 7. So you can just encode this number in binary or in hex as 0x7d0. And just a note on basis, we're going to use the notation 0b and 0x to denote numbers in binary and in hex, respectively. Okay, so let's see how to do addition and subtraction. The good news is that with positive numbers, this is just like in grade school. This is just like adding numbers in base 10. So in base 10, let's say we want to add 14 plus 7. Let's do this quickly. So you have 4 plus 7 is what? 11, right? So you put a 1 here and you carry 1. Okay, so you have a carry, right? And 1 plus 1 is 2. So you just put a 2 there. And yes, 14 plus 7 is 21. And why is Daniel telling us about this? We're all adults. Well, let's see. So let's do the same thing in base 2. What is 0 plus 1? 1. What is 1 plus 1? It's 0, right? It's 2, but that's 1, 0. And so we put a 0 and we carry 1. What is 1 plus 1 plus 1? It's 1, 1. So we take 1 and carry out 1, and then we have 1, 0. And so that's it. Now, if we look at this binary number, well, these two, by the way, are 14 and 7, of course. And so we get 16 plus 4 plus 1, so 21. Good. How about subtraction? So 14 minus 7, you don't put minus 3 in there. You say, well, I'll just borrow 1 and put a 7, right? Do 14 minus 7, 7, and then borrow 1. And minus 1 plus 1 is 0. So good. 14 minus 7 is 7. In binary, we have 0 minus 1 is what? Right. And you borrow minus 1. Minus 1 plus 1 minus 1 is 1, and you borrow 1. Same deal. And minus 1 plus 1 cancels out. So you have 0, 1, 1, 1. Again, 7. Okay. But we've only been talking about positive integers, right? So let's do a slightly more interesting case and subtract these two numbers. So this is 3 minus 5, right? 0, 1, 1 minus 1, 0, 1. So 1 minus 1, 0. 1 minus 0, 1. 0 minus 1, 1. And then we have a minus 1 here, which is going to show up as 1, 1, 1. And we can keep going forever putting 1s. But the point here is that we don't really have a way to represent this, right? These negative numbers yet. So what does this mean? What this means, what this partial operation is telling us is, well, this is minus 2 to the power of 3 plus 1, 0. Yeah, it's minus 8 plus 6 is minus 2, so that checks out. So the point is we need to find a way to represent negative numbers. Before we do that, let's actually take a step back and appreciate some nice properties that we get with positive integers. And in particular, we have what we call binary modular arithmetic. So if we use a fixed number of bits, and that's kind of necessary because there's no way to implement an unbounded number of bits in hardware, eventually you'll run out. And so we'll, in practice, manipulate 8-bit, 16-bit, 32-bit numbers. And so addition and other operations like subtraction may produce results that are outside of the range, right? For example, if you're adding two large numbers, you might run out of bits to represent them. And so in the example of addition, we'll take an extra bit. Other operations like multiplication can take many more bits. This, getting out of the range, is known as an overflow. And how do we handle the overflow? This overflow is quite crucial because it will happen somewhat often. So a common approach is just throwing away the extra bit and taking the 16 or 32 or m bits that we're considering. And this gives rise to modular arithmetic, which basically means that throwing the extra bit is equivalent to when you have m-bit numbers, just following all operations, addition, multiplication, and so on, with mod 2n, right? So doing all operations modulo 2 to the power of n, of the number of bits that you have. Visually, what this happens is that the way this shows up is if you consider all the possible numbers. In this case, I'm showing 3 bits. It's just like a clock. So addition is going clockwise in this diagram. So for example, if I have 0 and I add 2, I'll just be going 2 positions clockwise, and then subtraction is going counterclockwise, right? It's just going in the opposite direction. That's very nice. There's a good symmetry there, and we'll see how to leverage it a little bit later. And so in this case, just going back to the previous example where we saw, what do we do with that minus 1 borrow? What happens if we do 3 minus 5 modulo 8? Well, so we start at 3, and then we go 5 positions counterclockwise, and we get 6, 1, 1, 0. Right? So you can wrap around. In this case, we have an overflow, but it is all consistent. We're just going around. We're crossing 0. Okay, any questions? So ignoring the extra bits that we get just gives rise to modular arithmetic. And this, as we will see, makes things much simpler. So now that we have this modular arithmetic business in mind, let's see how we can go about encoding negative integers. The first attempt is we could just do what we do with pen and paper and use what we call a sign magnitude representation. So if we encode or if we add an extra bit, let's say the leftmost bit or the highest order bit here, to represent the sign, we could just choose 1 for negative and 0 for positive, and that way we'll know whether the number is negative or positive, right? Well, this is very intuitive because it's what we do with pen and paper. But it actually is not great. It's not very good in terms of efficiency. So what problems do you have with this encoding? Does anybody know? So one very glaring issue is that now we have 2 representations for 0, which is the same number. And so if you think about doing things like comparisons, now you need to see, it's not just are all the bits the same. It's like, well, and if it's 0, are these bits, these bits don't matter, right? So now that's going to result in more sophisticated circuits. But even worse, things like addition and subtraction now use different algorithms and are more complex. You need to look at different cases of is this number negative, is it positive? And so that results in fairly complex circuitry. So we had a good thing going on with modular arithmetic. So let's figure out if we can derive a better encoding. And this is actually, if we go back to this clock representation of numbers, let's see if we can just relabel some of the digits that we have here, right, 0 through 7, to represent negative numbers while retaining the nice properties of modular arithmetic. Can anybody tell me how would I go about just changing the meaning of some of these numbers? What numbers would you change? Yes?
Make half the circle negative.
Sorry?
Make 1/2 the circle negative numbers.
Right. But how? More specifically.
Well, 1/2, like the left half, for example, has the leftmost bit 1.
Mm-hmm.
So if the leftmost bit is 1, then the number is, the consequence of the number is a negative number.
So one thing to think about here is that if I just went by that rule, sign magnitude encoding is already doing that, right? Because the ones are on this half, right, and the zeros are on this half. So I'm looking more specifically about how do you relabel particular digits, right? So that we get modular arithmetic. And in particular, if we do 0 and we subtract 1 from 0, what number would we like to get? -1, right? Okay, what did we say subtraction was? Going counterclockwise, right? So if we change 7 by -1, that works, right? This still has all the properties of modular arithmetic. And then the question is, well, we can keep relabeling, and where do we stop? So, one approach is to stop at -4. And that gives us some very nice properties. The most obvious property is that all the negative numbers have a 1 in their most significant bit. But this actually makes the encoding very, very easy, as we'll see next. So this is called 2's complement encoding. And it actually leads to a very simple formula, where it's just like before, except we're taking the highest order bit, the leftmost bit, also called the most significant bit, or MSB, and changing the sign of the base, right? So the base for the most significant bit is -2 to the power of n minus 1, right? So you end up with a very similar formula to before. You retain this property that negative numbers have a 1 in the higher order bit. And the most negative number, in this case, is 1 followed by all zeros, right? Which is -2 to the n minus 1. What is the most positive number? Well, it's 0 followed by all ones, right? All positive bases enabled. And that's 2 to the n minus 1 minus 1. How about what number do you encode if all bits are 1? Sort of heard it. Anybody? -1. Perfect. So you have the highest base and then all the others essentially counterbalancing it. So the nice thing about 2's complement representation is that it makes arithmetic just very, very easy. Especially it makes addition and subtraction super easy. So first let's see how to negate a number. So if I give you A encoded in binary, how do you compute -A? And the procedure here is to invert all the bits and add 1 to the result. So let me just introduce the first Boolean operation. We're going to see a few. So, well, actually I don't know why I'm drawing it here. So the first Boolean operation is inversion, which we'll denote with an overbar. So if I give you an input x, not x, or overbar x, if x is 0, you want 1. If x is 1, that's 0. So why is it the case that if you can get -A given A by inverting all the bits and adding 1? Well, we just have to prove it through a little bit of manipulation of a couple of equalities. So let's say we start with -A plus A equals 0, which equals -1 plus 1, right? And now, if we reassociate terms and move this plus A term to the right side, then we can associate terms as minus a is minus 1 minus a plus 1. Right? And what is this minus 1 minus a? Well, we said that minus 1 was all ones, and minus a, let's just do minus a with subtraction. Right? So if you encode, so remember this number is in binary, so that you have bits A0, A1, up through a(n minus 1). If A0 was 0, 1 minus 0 is 1, right? And if A0 was 1, 1 minus 1 is 0. So 1 minus A0 is not A0. Is that clear? Okay. This is just a single bit, 1 minus a, or 1 minus x. So if x is 1, then you have 1 minus 1, which is 0. If x is 0, you have 1 minus 0, which is 1. And this is not x. Right? Okay, so that just makes this equivalent to inverting all the bits of the number. And then we add 1, just like this formula over here says. Now, you might be wondering why I'm going through all this effort of negating numbers. The reason is that now, apart from sometimes you actually do need to negate a number, now we can, to compute a minus b, we can use addition and get rid of subtraction. So all I've told you about borrows, forget about it. We'll just use a plus minus b and invert b. And though this might be a little bit, might seem a little bit arbitrary, as we'll see in a few lectures, the reason this is very nice is that we'll build a single circuit that can add and subtract, because this inversion is trivial and because adding 1 to a number is also very easy. And so we'll see that with some modifications, we'll start with an adder, and then by just changing a few things, a few very simple things, we'll be able to both add and subtract. So let's just do one example. Let's say we want to compute 3 minus 6 using 4-bit 2's complement addition. So 3 is 0, 0, 1, 1. 6 is 0, 1, 1, 0. And so if we invert all the digits and add 1, right, we have 6 is 0, 1, 1, 0. So if you negate all or invert all the digits of 6, you get 1, 0, 0, 1. And then plus 1, you get 1, 0, 1, 0. Right? So minus 6 is 1, 0, 1, 0. Let's put those two together. 1 plus 0, 1. 1 plus 1, 0. And we carry on. 1 plus 0, 1. And 1 plus 0, 1. And we get essentially 1, 1, 0, 1. Which is a negative, which is minus 3 in base, in 2's complement representation. Just quickly, we can go through this second example, 3 minus 2. This is actually interesting because we're not changing signs, right? 3 minus 2, we expect 1. But if we do minus 2, we get 1, 1, 0. And then if we just go through the motions here and do 1 plus 0, 1, 1 plus 1, 0, and we carry 1, 1 plus 1, 0, and we carry 1. And we get this 1 here, even though we didn't change sign, which might be a little bit confusing. So what do we do here, right? We expect to get 1. And remember, this is modular arithmetic, so we are always only going to keep the last 3 bits. We're using 3-bit 2's complement addition, or 3-bit 2's complement representation. You throw out everything that is out of range. And this 1 is just telling us that we crossed 0. So we started with 3, and then we went all the way through 0 by doing addition of negative 2, which is really 5 positions, right? Or 6 positions. Okay. So that's it for today. In recitation tomorrow, you'll see many more examples on 2's complement. And so in summary, we can encode and unsign integers using strings of bits. And 2's complement allows us to have very, very simple arithmetic. All right, thank you.